but not to Nairobi. So as I think the conjecture still holds. So
she's always welcome to come to Africa.
Yes. Yeah. No. It's not Africa now. It's changed. It's Nairobi. Yeah.
Okay.
Yeah. Great. Yeah. So I think we can give it like some few minutes, some people to join. People are a bit
sure.
Slow. I think like in my university, we are still in holiday, so it's different. I think Makerere, you're back,
right? Students are writing exams.
Oh,
others started. I mean, it's a combination of many things.
Yeah, there are so many people I haven't seen for a while. Like, I think I've not seen Sarah for a very long time. I think she's in the meeting. And many
you have not seen her physically, maybe.
At least I mean in the seminar, I've not seen her for some time. Hi, Sarah, how are you?
Hi, Jared.
How are you?
Fine, thanks. I'm sorry, I've been a little busy.
Yeah, so my conjecture is true. Yeah. Thanks, welcome. Thanks for coming. Welcome. Yeah, okay, so David, you take it over.
Yeah, yes, may I?
You can
spell that too. Meanwhile, display the slides. Okay. So I think we are getting late. People are still few, but I'm hoping more will join us along the way. So I take this opportunity to welcome you all to the seminar for today, which is going to be given by Dr. Spela Spenko. Dr. Spela Spenko is from the University de Brussels, which I think means Free University of Brussels in English. She will be speaking to us about the homological mirror symmetries and hypergeometric systems. Dr. Spenko, you are welcome to start.
Thank you very much. Thank you very much for the invitation. I'm very glad to speak in this seminar. I hope also to see you in person sometime soon in the future, and to invoke a bit of real space spirit. I included some artworks from Kenyan artists and from the artists of Slovenia, from the country where I'm originally from. So, as mentioned, I will talk about homological mirror symmetries and hypergeometric systems. So, and first we will start with a classical problem, namely Hilbert's 21st problem, which asks the following. So, show that there is an equation of the Fuchsian class with given singular points and monodromy group. So perhaps we should first decipher this problem a little bit. So what does it mean for a system of linear equations to be of Fuchsian type? So assume that we have a system of linear differential equations like this is of Fuchsian type if A of Z, so this is some matrix of functions in Z, and these functions should be holomorphic on C bar. So we add to C also infinity, except at finitely many points. A1 up to A capital N, where they can have a pole of order at most 1. So in particular, if we look at one differential equation depending only on one variable, y, then this is of Fuchsian type if and only if the familiar Fuchsian condition is satisfied. Okay, so then these were systems of differential equations of Fuchsian type. Then what is a monodromy? So assume that we have a system of linear differential equations as before, and A1 up to AN are singular points. So those points at which the matrix A of Z is not holomorphic. Then we take a closed path, gamma, in the complement of these points and C bar. And we know that this system of differential equations has locally, we know that there exists a basis of solutions. We denote them by y1 up to yn. And then we can analytically continue these solutions along gamma. So maybe to illustrate this a little bit, so this is one lake in Slovenia. So assume that we have one singular point, here represented by this island, and we take a gamma that goes around the island. Then locally, so on this gray area, assume that we have a basis of solutions, so y1 up to yn. And then when we analytically continue these solutions along gamma, we obtain new solutions, y1 tilde up to yn tilde. And so because both of these are bases of solutions, they should be related by an invertible matrix rho gamma. So rho gamma is in an invertible matrix in GLNC. It turns out that this rho gamma is independent of the homotopy class. It only depends on the homotopy class of gamma. So we obtain a map. It turns out to be a group homomorphism from the fundamental group of this of C bar without singular points to GLNC, which maps the homotopy class of gamma to rho gamma. And this is what is called a monodromy representation. So to maybe finish this discussion about the monodromy, let's look at a concrete example. So we take the differential equation zy prime minus alpha y is equal to 0. And so this differential equation has singularity at 0 and infinity. And we take a path around 0, so gamma. And so there is one solution locally of this differential equation. So y is equal to z to the alpha. And if we analytically continue this solution along gamma, we obtain another solution, y tilde, which is equal to the e to the pi I alpha z alpha. So then how our rho looks like. So we first notice that the C bar without 0 and infinity, so this can be identified with C without 0, and the fundamental group of this space is equal to Z. And we may take the homotopy class of gamma as the generator 1. So then this map, this rho sends K to the e to the pi I k alpha. So that's the monodromy representation corresponding to this differential equation. Okay. And now we can restate Hilbert 21st problem. So what is our input? We begin with capital N points in C bar. So that's first part of the input. And then the second part of the input is we take group homomorphism from the fundamental group of the complement of this capital N points in C bar to the GLNC. And here N is arbitrary. Or in other words, we just take one representation of this fundamental group. And then Hilbert asks the following. So does there exist a system of linear differential equations of Fuchsian type whose singular points are these points and that the monodromy representation coincides with rho? So given singular points and the representation of the fundamental group of their complement, we would like to find a system of linear differential equations that has this representation as the monodromy representation. Okay. So what has already been done on this problem? So first there was a solution proposed by already in 1908 by Slovenian mathematician Plemal. But it turned out that this Plemal's proof was not entirely correct. And a counterexample was found by Bollybrook. And among algebraic geometers, the focus was directed towards higher dimensions with a suitably rendered condition. So instead of the Fuchsian condition, one requires regularity, a weaker condition. So in the complex dimension 1, this means that on the punctured angular sector around the singular points, the solutions have moderate growth. So they don't grow too fast. And this also has an algebraic interpretation that generalizes to higher dimensions. And this algebraic interpretation was actually a cornerstone to a correspondence that we are going to see now. So that's so-called Riemann-Hilbert correspondence 1. So we take X a complex manifold and D in X a divisor. Then the Riemann-Hilbert correspondence 1 says that we have one-to-one correspondence, natural one-to-one correspondence between systems of linear differential equations on X with regular singularities contained in D and representations of the fundamental group of this complement. So let me just mention that this also holds in the context of smooth algebraic varieties, which might have been original motivation of the linear. And in short, we could say that topology, here measured by the fundamental group, is somewhat determined by analysis or algebra, here determined by systems of linear differential equations with regular singularities. Okay. And now, so this formulation here is not very precise. So we will now make it a little bit more precise, and we will refactor this. We will refactor this correspondence. So how can we get from this left-hand side to the right-hand side? So if we have a system of linear differential equations on X, so first we can restrict this system on the complement of D in X. And then we get a system of linear differential equations with no singularities. Okay. And then we can look at the solutions of this system. But we don't look only at global solutions, but also the local solutions. So actually, what do we get then if we look at the solutions, and that for every open subset, to every open subset, we associate solutions on this open subset, we actually get a sheaf of solutions. So this is a locally constant sheaf, and sheaves of finite dimensional C vector spaces, because locally we only have a finite dimensional space of solutions. And such sheaves, so locally constant sheaves of finite dimensional C vector spaces, are also called local systems. And then to go from local systems to the representations of the fundamental group, that's some this we obtained in a similar way that we obtained the monodromy representation. And so it turns out that all these sets can be enhanced to abelian categories, and actually also all these arrows are equivalences of abelian categories. And now we would like to generalize this to also other systems of linear differential equations, not necessarily those that have regular singularities on some divisor. And so to do this, we go here on the left-hand side a bit more still to the algebra direction. And so we will replace the differential equations with modules over the ring of differential operators. And with this, we enter the framework of so-called D modules. So assume that X in C to the n is an open set. And with O of X, we denote holomorphic functions globally defined on X. Then D stands for partial differential operators with coefficients in O of X. So in D, we have the following linear combinations, where here the coefficients Fi belong to O of X. So our holomorphic functions globally defined on X. And now if we take a P, a differential operator, so an element in D, then we can associate to it a differential equation and vice versa. So for example, if we take the differential equation that we had before, so zy prime minus alpha y equals to 0. So to this, we can associate the differential operator partial z partial z minus alpha. Okay. And then the solutions of these differential equations correspond to the holomorphic functions such that P of u is equal to 0. And even more algebraically, we can represent this as the homomorphisms of D modules from D mod dp to O of X. So maybe how does this isomorphism look like? So assume that we have a holomorphic function u in here such that P of u is equal to 0. Then we can construct a homomorphism of D modules which sends D to D times u. Okay. And so we need to check that this homomorphism is well defined. And that's and that's because P of U is equal to 0. So then indeed, dP maps to is dPu maps to 0. Okay. And then to go in the other direction, assume that we have a homomorphism on this side. So because this homomorphism is a homomorphism of the module, is also determined by its image in 1. So phi of 1 and phi of and so we need to check that P of phi of 1 is equal to 0, and that's because phi maps from d mod dP. So phi sends dP to 0. Okay. So that's this. That is the correspondence, and we can also generalize it to collection of differential operators in D. So then the solutions of the corresponding system of differential equations is isomorphic to the homomorphisms of D modules from M to O of X, where M is now defined by this exact sequence. So we have well found a correspondence between systems of differential equations and D modules, finitely presented D modules. But as already mentioned before, we are not only interested in in D modules, and moreover, there is also one-to-one correspondence with the global solutions of these systems of differential equations. But we are not only interested in global solutions, but we would like also to know something about local solutions. So then we need to bring in again this tool that takes into account also local solutions. So we should transform everything into language of sheaves. So here, instead of O of X, we take O, which is a sheaf of holomorphic functions on X. So to an open set, so O of U for an open set in X consists of holomorphic functions globally defined on U. Then also D we replace with curly D, which it's a sheaf of partial differential operators, which to an open set U in X associates partial differential operators with coefficients in O of U. And then instead of the homomorphisms of D modules, we then take the sheaf of homomorphisms, which to an open set U associates the homomorphisms of DU modules from M of U to O of U. Okay. So in this way, we also get hold on local solutions. But there is another caveat to consider. Namely, we would like maybe to compare the solutions of different systems of differential equations. Perhaps say something about the solutions of the union of two systems of differential equations. But here we encounter a problem that this solution functor, so which solution functor is not exact. So therefore, we should also take into account higher solutions, namely extension modules. And it will turn out that these higher solutions already give us all the information that we will want. But maybe now it's a good place to ask ourselves, what kind of sheaves these are. So we know that there are sheaves of C-vector spaces, but is there maybe any other property that distinguishes them? So this will be the case if we restrict to some nice kind of sheaves of D modules. So here say that if here we restrict to the holonomic D modules, which roughly means that the solution spaces and higher solution spaces are all finite dimensional. Then the higher solutions are constructible sheaves. So if we recall from the Riemann-Hilbert correspondence one, so when we look at the solutions there, then we got local system. So locally constant sheaf of finite dimensional vector spaces. And here with this, here that we look at more general M, we get sheaves that are built from local systems. So they are called constructible, which means that there exists a stratification of X into a disjoint union of X alpha, such that Fi restricted to X alpha is a local system. Okay. So now we gathered quite a lot of information. So we have on one side, we have this sheaves of D modules on the algebraic side, and then on the topological side, we have solutions, we have higher solutions. To compute those, we also need to know something, again, on the algebraic side about the projective resolution of M, and convenient machinery to take all this data into account and not to lose too much information is the derived category. So assume that A is an abelian category. For example, the category of modules. In our case, we had the category of the X modules, or the category of C vector spaces on X. Then with C of A, we denote the category of complexes. And in this category of complexes, we would not like to distinguish, we have the category of complexes. And so the map between them are also maps of complexes. And we say that the map F between X and Y, so between two complexes, X and Y, is a quasi-isomorphism if it induces an isomorphism on cohomology. And we would not like to distinguish between the complexes that are related by a quasi-isomorphism. We would like that they become isomorphic. So therefore, we just formally invert all the quasi-isomorphisms. So this is similar to the localization in rings. And then we get so-called derived category. And also, if we have a functor between two abelian categories that it's left exact, then it induces a derived functor between the corresponding derived categories. So if we look at this on our example, so what do we have? So F in our case is this solution functor that goes from the category of D modules to the category of sheaves of finite dimensional C vector spaces, or sheaves of C vector spaces. And then this induces a derived functor from the corresponding derived categories. So from one derived category to the other derived category. And this derived functor actually captures all the information about the higher solutions. So the cohomology of this functor is given by the higher solution sheaves. Okay. So now with this we have all machinery so that we can state the general Riemann-Hilbert correspondence in its full power and complexity. So we will look at the the derived category of dx modules, and in this derived category we restrict to those that have regular and holonomic cohomology. So, and basically this means that that the corresponding solutions spaces should be finite dimension. So this is on the algebraic side, and on the topological side we restrict to those complexes that have constructible cohomology. So if you just recall, constructible means that it's built from local systems. So locally constant sheaves of finite dimensional C-vector spaces. And then, so the general Riemann-Hilbert correspondence says that the derived solution functor induces an equivalence of derived categories. So perhaps it's good to that we pause here a little bit. So this is really a vast generalization of the Riemann-Hilbert correspondence that we have seen before, and it allows to associate, in particular, to any D module, a topological object, a complex of sheaves with constructible cohomology. And also maybe a remark that we really need to pass to the derived level, because as we have seen, the solution functor is not exact. And then maybe let me also mention something that we might need later on. So if we just look at the image of this derived solution functor evaluated only on the abelian category of D modules. So in this case, we get on the topological side, on the right-hand side, some special complexes of sheaves, which are called Pervol sheaves. So not to be confused, they are not actual sheaves, but they are complexes of sheaves. And now, slight change. So now we divert our story to mirror symmetry. And there we will encounter some representations. And our aim will be to try to realize them as the monodromy representations of some differential equations, some systems of differential equations. So let's first very briefly say a few words on mirror symmetry, a theory that has its origin in physics, or more precisely in string theory. So this is a cross-section. This is a real picture of a cross-section of a space that appears in string theory. And spaces in string theory have both complex and symplectic structures. And they come in mirror pairs, where the complex and symplectic structures are interlaced. So the complex structure of X corresponds to the symplectic structure of X naught, and vice versa. So now assume that we start with X as a complex manifold. So we fix the complex structure of X. And with this, we fix the symplectic structure of X naught. And then we still have some space for the complex structure of X naught. And with K of X, we denote the space of complex structures on X naught. And then the conjecture from homological mirror symmetry says that the fundamental group of this space of complex structures on X naught should act on the derived category of X. And here one can think of the derived category of X just as the category of bounded complexes of vector bundles on X. And as a corollary, we guess that the fundamental group of K of X also acts on the complexified Grothendieck group of X. And this is sometimes a finite dimensional vector space. So, and it's this action for which we will wonder to which system of differential equations it corresponds to. Okay. But now we first look at an example that will be somehow running example till the end of this talk. So we look at the conifold. So we can define the conifold as a hypersurface in C to the 4. So it can be just defined by this equation in C to the 4. Okay, and then so this will be Y, the conifold, and then for X we take some nice resolution of Y. So if we would like to see this in the toric world, so how shall we represent Y? So Y we represent as a cone over a unit square. And to get X, we should also additionally add this diagonal hyperplane. But there is yet another viewpoint that will be more useful to us. So assume that we have an action of one-dimensional torus to the on the four-dimensional C vector space. And assume that the action is the following. So T from C star acts on this 4 tuple of points in C to the 4, x1, x2, x3, and x4, such that, so it's T times this tuple is T inverse x1, T inverse x2, T x3, and T x4. So that's the action. And we can actually obtain Y as the quotient for this. So our Y, the conifold, is isomorphic to the quotient of C to the 4 by this action. And to get X, we should first remove some undesirable locus from C to the 4, and then again take the quotient. And in this case, the physics heuristics tells us that K of X, so the space of complex structures on X naught, is P1, so projective line without 3 points, 0, 1, and infinity. And and we can think of the derived to get hold on the derived category of X. It's better to see it embedded into the derived category of modules over the polynomial ring in 4 variables. Those modules that also have an action of C star, and they are equivariant for this action. So they also have an action of C star, or equivariant for this action, or equivalently, we can also say C star equivariant OC4 modules. And the image of this embedding is generated by the structure shift, and structure shift tensored with one-dimensional representation with character 1. Okay, and so that's, this part is not it's not really important, but it just helps us to write the action of these three generators in P1 of K of X on the derived category of X. So in this basis, the action is given by the following three matrices. Okay. And it's also this viewpoint, so an action of a torus on a finite dimensional C vector space that we will pursue, because in this case the heuristics about K of X is rather reliable. But what we will need to assume is that our action is symmetric enough. Okay. So this is now our general setting. We assume that we have a representation of an n-dimensional torus on the d-dimensional C vector space. And the X that we will be looking at, so this is somewhat the principal variety for which we will try to we will try to consider the homological mirror symmetry conjecture, is obtained as similarly as in the case of the conifold. So first we remove from C to the D some undesirable locus, and then we take the quotient. And then the heuristics again tells us that K of X is in this case a complement of a hypersurface in the n-dimensional torus. The n-dimensional torus that acts, the acting torus. Okay. But this complement of the hypersurface, or rather hypersurface itself, might be rather complicated. But it turns out that in nice situations, so namely, if this action is sufficiently symmetric, so-called quasi-symmetric, then K of X is a complement of a hyperplane arrangement. So much more concrete space. And so maybe let's make a quick sanity check for the quick sanity check in the example of the conifold. So if we assume that X is a small resolution of the conifold, then on the previous slide, we have seen that K of X is in this case the projective line without 3 points, which we may also view as the C without 0, identified with C without 0 and 1. And then we, if we apply this logarithmic coordinates, which means that we just apply 1 divided by 2pi log to all the points here, we obtain C without Z. So indeed, we obtain a hyperplane arrangement, because so what is a hyperplane in C? A hyperplane in C is just a point. And we obtain a hyperplane arrangement that is an infinite, but locally finite. And this will also be the case in general. So a take from this slide is that in the case that the action is symmetric enough, then K of X is much simpler, is a complement of a hyperplane arrangement. Okay, and then in this setting, in the setting of a nice symmetric, quasi-symmetric action, in this case, Halper and Leistner and Sen, they confirmed the homological mirror symmetry conjecture. So in this case, the fundamental group of K of X indeed acts on the derived category of X. And maybe just for the information, that this can be also generalized to some other reductive groups, not necessarily, we don't need necessarily to have here only a torus. Okay, and as a corollary of this, as already mentioned before, we get that this fundamental group also acts, so P1 of K of X also acts on the complexified Grothendieck group of X. And this, in this setting, is a finite dimensional C vector space. And so what we will be doing in the rest of the talk is that we will try to find a system of differential equation that for which this representation is the monodromy representation, or system of linear differential equation that realizes this representation as the monodromy representation. Again, we first look at the conifold, and there we take a bit ad hoc maybe, we just take a Gauss hypergeometric equation. So that is this differential equation. And then one can compute monodromy. I think there is the monodromy described also on Wikipedia, and one gets the following three matrices. And then if we set A, B, and C equal to 0, we get the same matrices as we have seen before. And from this, one can conclude actually that this action, in the case of the conifold, corresponds to this differential equation, which is just Gauss hypergeometric equation after setting A, B, and C equal to 0. Okay. And now we change our focus a little bit. So now we would like to see, so this action originally comes from the action of P1 of K of X on the derived category of X. And we would like to see whether we can somehow tweak this action in order to obtain a Gauss hypergeometric equation also for other parameters, A, B, and C, not only for A, B, and C equal to 0. Okay, to do this, we first notice that actually also four-dimensional torus acts on the C to the 4 just coordinate-wise. So we have T1, T2, T3, T4 acts on X1, X2, X3, and X4, just as T1, X1, T2, X2, T3, X3, and T4, X4. Okay. And the one-dimensional torus that we had before just embeds into the four-dimensional torus, and the embedding is induced by the action. Okay, and this inclusion of one-dimensional torus to the four-dimensional torus splits, and the complement is a three-dimensional torus. So we seem to be good. We seem to be good on the way, because here we have as the complement a three-dimensional torus, and before we had three parameters, A, B, and C. Okay. So to get an action also for other A, B, and C, we need to replace dB of X by a bigger category, d tilde, such that the character space of this complementary three-dimensional torus acts on it. So the construction of this d tilde is maybe a bit too technical, but it turns out that P1 of K of X still acts on d tilde. And moreover, because this character space acts on d tilde, we get that the Grothendieck group, complexified Grothendieck group of d tilde, is a module over the group algebra of this character space, which is moreover isomorphic to the coordinate ring of the three-dimensional torus. And if we now specialize this K0 d tilde at one point in the three-dimensional torus, we obtain the Gauss hypergeometric equation with these parameters. Okay, so we can indeed obtain also the Gauss hypergeometric equation for other parameters. From an action of the fundamental group of this K of X on some derived category. And now we would like to generalize this to higher dimensions, to more general actions. And for this, we first observe that or we recall the famous solutions to Gauss hypergeometric equations. So they are given by hyperfunctions, and there exists a generalization of hyperfunctions to higher dimensions. So the multidimensional hypergeometric functions, they look like that, and then the generalization of Gauss hypergeometric equation is dictated by the desired solutions that we would like to obtain as the solutions of these generalized Gauss hypergeometric equations. And these solutions should be given by multidimensional hypergeometric systems. And then one obtains so this was maybe the original construction of GKZ, or original motivation for the construction of GKZ hypergeometric system of differential equations. And GKZ because they were discovered by Gelfand-Kapranov and Zelevinsky. Okay. And now you may already guess what now the result will be. So in the case that we have in the general case, if we have the action of P1 of K of X on the complexified Grothendieck group of X, it gives the monodromy of a GKZ hypergeometric system. So this statement is it's not entirely correct. So what we should actually do is that we should, as before, in the case of the conifold, replace dB of X by a bigger category, d tilde, such that P of 1 of K of X still acts on the Grothendieck group of d tilde. And after specialization, we obtain the monodromy of GKZ hypergeometric system. And this also gives us GKZ hypergeometric systems for different parameters. Okay, it turns out that this monodromy and the action on the derived category of X can be also generalized a bit further, lifted a bit further. So this comes in the context of so-called perverse Schobers, perverse sheaves of categories. But maybe let me just stop here. And thank you very much, Asante.
Yes, thank you, Asante Sana. At this point, you are welcome to ask questions. I saw one in the chat. Is there a condition on the T's? I guess that was some action by T.
So the action, I guess, first appeared here, but.
Okay, there's another T here. I don't know whether he meant. Okay.
Yeah, actually, I meant the one you wrote by hand, the TI subscript I's.
So the 4-dimensional, this one?
Yeah. So
No, so this is just an element of C star to the 4. And this element acts on an element in C to the 4, just like this, just that it's the coordinate action.
okay, that's just scaling so you don't amplify.
Yeah, there are
Yes,
no.
any more questions? Yes, I have some 2 questions. There is some action which you called quasi-symmetric. What do you mean by quasi-symmetric?
Yes, I didn't explain this, but thank you for the question. So maybe I just, yeah.
Yes.
Okay, so this means that so the action is determined by the weights, by the elements of x c star to the n. And so it's in this. So, for example, in the case of the conifold, where the action of the was like that, is T inverse x1, T inverse x2, Tx3, and Tx4. Then the weights are. So here we have -1 because it's T to the -1, again -1 and 1 and 1. Okay, so then we have these weights, then the quasi-symmetric, it means that for every line, and this is also isomorphic to z to the n, okay? So for every line in r to the n that goes through the origin, the sum of beta i's that lie on this line is equal to 0. So for example, if we have this, for example, 2-dimensional torus, and then this would be the weight, this quasi-symmetric, because here we have 3 lines on which a weight lies, and then on all those 3 lines, the sum of the weights is equal to 0. But then if we, for example, take the action with these weights, something like that, then we see that this is not quasi-symmetric because, for example, already on this line, the sum of these 2 weights is not equal to 0.
Okay. Yeah, so thank you. Yeah, and 2, I have heard about homological mirror symmetry as something that comes from physics. Do you think it is possible to, in these few minutes remaining, to tell us the relationship between what you've talked about and the physics? How does the physics come in? I understand.
Yeah, unfortunately, my understanding of that is not sufficient to say something sensible.
All right, thank you.
Sorry.
I guess there are no more questions. If you want to know more about what Spela has shared with us, she's reachable on email. You can always email her. We thank you, Spela, for sparing time to talk to us about homological mirror symmetry. Please let's unmute and thank Spela by clapping.
Thank you.
Number 3.